Before this section, if you need a refresher of factoring, please make sure that you watch the optional video on factoring that has been posted. So we want to solve the equation 4 cosine squared of x minus 5 cos x plus 1 equal to 0. Because this equation is quadratic in form, we will need to factor this equation. There are many ways of factoring. I'm going to use the method that I showed. So in this method, and once again, you can watch the full factoring video to learn what I'm doing. I'm just going to go through the actual process. So I'm going to multiply 4 times 1, which is 4. The middle term is negative 5, so I'll put that at the bottom. I need to find two numbers which multiply to 4, add to negative 5, and those numbers are going to be negative 4 and negative 1. They multiply to 4, add to negative 5. Then I take my coefficient 4x, write that on top of both of these to make it into a fraction. Now at this point, we have 4x over negative 4, and we have 4x over negative 1. Remember, we have to reduce these. So if I reduce this one, this is going to give me x over negative 1. This one cannot be reduced, so it stays as 4x over negative 1. And then the x's kind of fall over. So we have x minus 1 times 4x minus 1 as the factored form. But instead of x, we have a cosine squared of x. So when I factor this, instead of x minus 1, I'm going to have cosine of x minus 1. And instead of 4x minus 1, I'm going to have 4 times cosine of x minus 1. And if you FOIL this back, you get 4 cos squared x. Negative cos, negative 4, that's negative 5 cos x. And then you have a positive 1. And this equals to 0. Now, the zero product property tells us that if two terms multiply to 0, then either the first one or the second one or they both have to be 0. Otherwise, there's no way for two terms to multiply to 0 unless one of them, at least one of them, is equal to 0. So according to the zero product property, we're going to say cosine of x minus 1 equals to 0, or 4 times cosine of x minus 1 equals to 0. Okay, it said each of these parentheses equal to 0 according to the zero product property. For the first one, we have cosine of x equals to 1. And then if I get the cos x by itself, I'm going to get cosine of x equals to 1/4, which is equal to 0.25. Now, our objective is to solve both of these equations. For cos x equals to 1, I know that whenever cosine or sine equal to 1, I'm going to get a quadrantal angle. Let me repeat that. Whenever cosine or sine of x is equal to 1, I am going to get a quadrantal angle. So on my unit circle, I want to know, so if I draw my unit circle, I want to know cosine is associated with the x value, so which angles have an x value of 1? So this point is 1, 0, this point is 0, 1, this point is negative 1, 0, and this point is 0, negative 1. So I want an x value of 1, which is going to be at 0 radians. And then we just want solutions between 0 and 2 pi, so I'm not going to write the general solution. But if I were to, just as a quick recap, the next time I get to an x value of 1 is when I make a full revolution. So that would be plus 2k pi, but I'm not doing that because I just want the solution between 0 and 2 pi. So x equals to 0 is going to be one solution. Now for the second one, I have cosine of x equals to 0.25. In order to solve this, I'm going to be using my xy coordinate plane. So I ask myself, where is cosine positive? So we have all students take calculus, and cosine's positive in quadrant 1 and quadrant 4. So those are the two quadrants we're going to draw triangles in. So we have one angle here, and we have another angle here. So I want to find the reference angle. To find the reference angle, I'm going to take the inverse cosine of both sides. Now on the left side, I have cosine of x. On the right side, I have a 0.25. So the inverse cosine, they cancel each other out. We get the x by itself, which is what I want. And if I take the inverse cosine of the left, I got to take the inverse cosine of the right. So I take the inverse cosine of 0.25. And if I do that, that's going to give me 1.318 in radian form. Now, just as a quick refresher, any reference angle, it has to be between 0 and 90 degrees. In radian form, that's going to be between 0 and 1.57. So this is between 0 and 1.57, which means this is a valid reference angle. Okay, so my reference angle is going to be 1.318. Actually, you know what? I should be using 6 decimals. So I apologize. I should be using 6 decimals and not 3, which I have said before, and I just need to be better about following. So I have so if I take the inverse cosine of 0.25 and I put 6 decimals, that's 1.318116. Until the very last step, use at least 6 decimals to make sure that you don't get a rounding error. Now we got 2 different angles. The first angle is the quadrant one angle. It's going to be this one here, and that one's easy. It's just going to be 1.318116. My second angle is going to be the angle that starts at the x-axis, always in standard form. But then this one goes all the way around to the terminal side, which is going to be this side. So here's what I know. I know the whole circle is 360 or 2 pi. So if I take 2 pi and I subtract off 1.318116, then that's going to give me 4.965 radians as my second angle. So I have 3 solutions. My 3 solutions are, and I'm going to write them in order. My smallest solution is 0. My smallest solution is 1.318. And my next smallest solution is 4.965. These are my 3 solutions. So my solutions, it means that if I take these 3 values and I plug them into my original equation, then the left side will equal to 0. And you can check this. You can go to like desmos.com, or you can put this in a calculator. You can check it, and this will be a true statement. Now the question says the smallest non-negative radian solution. So our smallest solution is going to be 0. And the next smallest non-negative solution is 1.318. They don't want the largest one. They just want the 2 smallest solutions. So for this problem, if I kind of break it down from start to finish, we factor the quadratic. After we factor, we use the zero product property to set cosine of x minus 1 equal to 0, for cosine of x minus 1 equal to 0, and we get cos x equals to 1 and cos x equals to 0.25. From there, we solve these as we did in 3.3 part A. Let's take a look at the next one. We have 2 sine squared x minus 3 sine of x plus 1 equal to 0. Now this time they want all solutions. So let me go ahead and factor this. So if I multiply 2 times 1, that's equal to 2. And my middle term is negative 3. I need to find 2 values which multiply to be 2 and add up to be negative 3. Those are going to be negative 2 and negative 1. Luckily the factoring in this section is pretty easy. Then I just take my coefficient, which is 2. So I put a 2x on top of each one, and then I reduce it. So 2x over negative 2 reduces to x over negative 1. And then I have 2x minus 1, that can't be reduced. So then these both fall over. So when this falls over, it becomes x minus 1. When this falls over, it becomes 2x minus 1. But because we have a sign, instead of saying x minus 1 and 2x minus 1, we're going to say sine of x minus 1 and 2 times sine of x minus 1 equals to 0. Zero product property tells us that sine of x minus 1 is equal to 0, or 2 sine of x minus 1 is equal to 0. And now we have to solve both of these. So for the first one, anytime sine or cos, so if I get the sine by itself, I'm going to get sine of x equals to 1. And then on the other side, I'm going to get sine of x equals to 1/2. if I solve for sine of x. For the first one, I can use a quadrantal angle, because anytime sine or cosine is equal to 0 or 1, I'm going to get a quadrantal angle. So if I write my points, this is 1, 0, this is 0, 1, this is negative 1, 0, and this is 0, negative 1. So I ask myself, sine is associated with the y value, so which angle has a y value of 1? And that'll be this angle. Something just happened. This angle is pi over 2. So my first solution is going to be pi over 2. And then if you notice, to get back to another y value of 1, I make a full revolution. That's 360 degrees, or 2 pi. So my general solution here is going to be pi over 2 plus 2k pi. Now on the other side, you have two options. Okay, you can use a calculator if you want to, but we don't need to, because sine of x equals to 1/2. That's one of our special right triangles. It's a 1 radical 3 2 right triangle. Okay, so let's go through and figure out where is sine positive. Sine's positive in quadrant number 1 and also in quadrant number 2. This is where sine is positive. Sine is opposite over hypotenuse, so my opposite is 1 and my hypotenuse is 2. The missing side is going to be radical 3, because you can use the Pythagorean theorem if you wanted to, but 1 radical 3 and 2, that's one of our special right triangles, so the missing side will be radical 3. Now our job is to figure out what is the reference angle x. So the reference angle x is going to be opposite of 1 in a 1 radical 3 2 triangle is 30 degrees. So our reference angle x is going to be 30 degrees. Then we have to find the measure of these angles in standard position. So the first one is just going to be 30 degrees. And the second one, so we're starting here. This is our terminal side. So if I take 180 minus 30, it'll be 150 degrees. And I can convert these into radians. This will be pi over 6. And then this will be 5 pi over 6. Now we want general solutions. So in order to get back to this terminal side, let's say we're talking about this first angle here. If I make a full rotation, I get back to that same terminal side. So we can just add 2k pi to each of these to get all the general solutions. So my solutions are going to be pi over 6, 5 pi over 6, and pi over 2, plus 2k pi, because if you make a full revolution on any of these, if you go 360 degrees, you get back to the same terminal side. And therefore, that angle will have the same exact value of sine as its coterminal angles. Okay. So if you have any questions on those, let me know. And then the next two problems we are going to be doing in class.